I want to talk about a concept which I've rather grandly called the Sadram architecture. And I would normally avoid such grandiose terminology, but the more I've worked on this, the more I've become convinced that this is practical, revolutionary, and will in fact change the way we think about computing. Only those first two propositions will I have time to defend in this talk. So, why do we need a new architecture? What's the motivation for that? Well, in the words of Moore's law, the golden age of Moore's law is over. Thus spake Pat Gelsinger, ex-CEO of Intel, quite recently. He went on to say that, well, perhaps we would be able to sustain a rate of doubling every 3 years instead of doubling every 18 months, which is the spectacular rate that we've seen over the last 50 years. Jensen Huang, a founder and CEO of NVIDIA, was a little more pessimistic. He simply said, Moore's law is dead. Dead. So whether we like it or not, we're going to have to cast our net a little bit wider in terms of where performance is going to come from. If we're blocked pretty much on the CPU end, then we need to go somewhere else. That's a tautology, obviously. Where are we going to go? Well, about the only place you can go is to memory. So, in terms of what I'm going to talk about, I'll discuss what and how Sadram is, some extensions that we're making to the GCC compiler to exploit those extensions. And in a sense, I've covered the first point. Why do we need this? And then the applications, the most important part of the whole discussion, I'm going to say I don't have time to discuss, right? But in an audience like this, I suspect that you'll see the point instantly. So, what is Sadram? Well, you've seen already. Well, why do you want to go to memory? Well, it's the largest number of transistors in any system. It's usually the largest cost element. That may not be true if you're an individual buyer, but if you're one of the big data centers, that's where you spend most of your money. It's a significant sink of heat, half of which is moving data from the memory to the CPU. That strike you as a little bit ridiculous? That half of the energy that memory consumes is just moving it from one place to another. So if we can avoid some of that movement, we've got some advantages built in. And here's the kicker. It is the principal constraint on system performance. Thus spake Roger Seitz 30 years ago. And what have we done in those 30 years? Nothing. We're still flogging the CPU horse, the multi-core horse. And you can throw as many multi-cores as you want. And finally, it's not going to matter a lot because they're just going to fight. You may, in fact, make it worse because you're going to increase contention for memory. And here's a highly technical description from a very senior engineer at Micron when we were talking about this in the brief period of time that I was at Micron until they fired me, thank God. Memory is made from shitty transistors. Okay. It's a little harsh, But, and if I might interpret what he said, memory transistors are made to hold data. The silicon is doped in a way that minimizes the transmission out. CPU transistors are designed to move data. Those roles are incompatible. There is no middle ground. So if we think we're going to take some functionality away from the CPU and move it to memory, it better be simple. Dirt simple. Because these shitty transistors ain't going to do it for you. We all pretty much know what DRAM is. A vast array of capacitors, each fabricated with a transistor, the so-called 1T, 1C model. There are other models, but almost all DRAM is 1T, 1C. Some decoders are organized into rows. When you select a row, the select line here, all these transistors turn on, discharge their capacitors, and it's gathered in the row buffer. This is the retail end of the DRAM business. This is where the processor gets its data and where it puts its data when it's going to be written back, and it's wide. 2 to the 13 bits wide, 8192, 256 32-bit words. There's your parallelism. Right there, what I like to call the intrinsic parallelism of DRAM. If we can figure out how to do something useful in this DRAM row buffer with the shitty transistors that we've got, that's going to be a win. And that's what Sadram's all about. The idea is to, and let me warn you, I'm talking conceptual issues here. There's some practical ways of doing this which will turn out to be somewhat different, is to put an array of comparators across the row buffer. The fancy entry to make the point that the idea is to keep the row in sorted order. If I just throw data in here at random, then it's much more difficult to find when I want to get back, when I want to get it back. So rather than a chaotic method, we impose an order on the DRAM in the way it represents the data, or the way it stores the data. Based on that vector of comparators, I can take a target word and compare it simultaneously with every word across the DRAM row. I can determine that this incoming word is larger than alpha, good, and help, and belongs in front of the word quit. And if I have some ability, a pipeline to move all this data to the right, then I can keep the row in sorted order. This is 250, if we're talking 32-bit words, 256-bit wide. So on the face of it, I have a 256 times multiplier versus doing such computations in a processor, where I've got to move the data to the processor and do something and store it back. As it turns out, the row will typically be 75% full, so our real power to weight ratio is probably about 200. And for the memory engineers, the ones that are holding their heads in their hands, no. The idea of putting a 32 wide bus right across the DRAM row, ouch, that's a lot of wires, a lot of connections, 8,000 connections. Well, it turns out we don't need to do that. Anybody that's represented this as parallel is actually cheating and lying to you, because it actually comes down to a prefetch buffer. It then passes through an ECC correction, which is essentially a linear process. So if we hang this comparator on the back of the ECC, we can do it practically for free. By simply chopping this 8192 down to 2048, my company, Pico Computer, made an FPGA controller for that, which we delivered to Micron on time and working for the show that they wanted to announce this new memory for. And on the strength, Micron was so impressed that they offered to buy out the company, which I accepted for better or for worse. Eventually the product was dropped for the very simple reason that if you make it shorter, if you make it very long, then you finish up this 8192. Why not make it 65,000? Why not make it 32,000, the size of a Linux page? Wouldn't that seem like a nice natural number? Well, if you make it much longer, then you're pulling down a lot more stuff that you just don't use. If you make it much shorter, then you've got to do multiple accesses to the memory in order to get the data that the processor wants. Low latency memory failed because essentially it lowered the latency. No two ways about that. But you had to do multiple accesses to get the same data because for some reason this 8192 is a Goldilocks number. Not too big, not too small. If you bring this much down, the processor will, with some fair probability, make multiple accesses of that DRAM row. You're either processing a string, you're marching along that DRAM row, you're processing elements of an array, you're marching along that DRAM row. Any number, you're loading a structure, again, the structure spreads across this piece of the DRAM row. You can do a lot in 8192. So that's a good size, and that's a good place for Sadram to inject its technology. The second component, namely the move, is a little more difficult than the comparators. As I said, we can practically reduce that to zero footprint. But that's not true of the move. We're going to have not a point-to-point bus all the way across, drivers and receivers at the beginning and end, each one, so really 16,000 such components. It's starting to get pretty expensive, and the notion of driving a 32-wide bus across the entire memory is a little bit expensive. As it turns out, there is a way to fix that, and since I'm currently applying for a patent for that, and I'm out of time anyway, I will not talk about that. Okay, so I can keep a row in order. I won't describe you that I can put secondary and tertiary and maybe quaternary structures above that, and keep a whole, drum roll please, an entire block in sorted order. Whoop-de-doo. So I can do sort in memory, eh? Why do I care? Whoop-de-doo is right. 25 to 50% of all computer cycles are spent doing sort. So the first thing I did when I moved to Boise, to Micron, as I asked them, Micron, is this still true? Nobody knew. So I went out. Knut discovered this by talking to manufacturers of computers. So I went out and talked to users. Said, you still spend 25, 50% of your time in sort? The answer was stunning. Easily. Easily. That shouldn't really surprise us. Sort is our most fundamental organizational tool. If I've got 1 million items and I'm looking for one, I'm going to have to look through 500,000 items. If I sort it and use a simple binary chop, I can do it in 20. Now, if I use some of the Sadram techniques, I can do it in 3. So we're talking a 500,000 to 3 ratio. Let's just call it $100,000 between friends and not argue about the chump change. And that's an organizational thing. If a memory is equipped with this technology, sorting becomes almost free, certainly free from the perspective of the CPU. Yes, there'll be some conflict for memory between the CPU and this. But literally, we can take a block of data, roll it in off disk, if such things still exist, or generate it from an algorithm, or pull it from some real-time observations. And when we finished writing that data to disk, to RAM, it's sorted, what I call free sort when I put on my promotional hat. So, yes, sort is a big deal. But let's look at this slightly differently. So as we turn this thing upside down, so as we think about not taking a block of data, rolling it into memory, doing some magic, and then now we can step through the data with a linear sequence in sorted order. But we look at the keys and think of them as the primary access token. So literally, we pass the text, help, or a word with all that stuffed into it, into the memory, and it comes back with the help. Well, some datum associated with this are pointed to another record or whatever it points to. All done without CPU involvement. You recognize that as a fundamental function of database, to map keys or tokens or whatever you want to call them to records. So now we're in the position to understand this word Sadram. It's either self-addressing DRAM or symbolically addressed CRAM, whatever, it's Sadram. Okay. Now sort is sort of a thing unto itself, right? You have a program, you call sort, qsort, or whatever you got, right? And it goes off and does its thing, and then you read your records or do whatever you're going to do. And when we start thinking in terms of using the key to access data, it opens up a whole can of worms. We really need to provide hooks in the language to be able to access memory by token. And that's why we're looking at, and this is a work in progress, so anything I say here can be taken with a grain of salt because it may change tomorrow. Essentially, I can see some stirring there, I better be quick. We're going to add a new organizational type called a SART, along with arrays and structures. That's the only two organizational types. And we'll access it with a key, and we'll add an operator freshly stolen out of APL. So there you have it. There's some SARTs. Why do we need it? Well, how it works, okay. Changes to C++, very glib treatment. And I'll throw it open to questions and suggestions, laughter, brutal criticism, all welcome.